So let's work this problem, and rather than write it out in a bunch of words, I just drew a picture of it. So take a look. We've got a spring here. It's got a pretty good spring constant, 500 newtons of force per meter, and we're going to shove this thing back so that we've compressed the spring to the left by 0.3 meters. And this has 20 kilograms, and then we're going to release it. Now it's going to start from rest, but we want to know when the back end of this crate gets to x equals 0, how fast is it going? So, and that's when, and now in part A, we want to know how fast it's going when x equals 0, when mu equals 0, that is there's no friction, a frictionless surface. But then for part B, it gets complicated because now we've got friction of, let's say we got a friction 0.3. So how are we going to do that? All right, so let's start with part A. Now I'm going to use energy to solve this. And this equation is not in your book, unfortunately. I love it. It's one of my favorite equations in physics. The work done by a non-conservative force is equal to the change in mechanical energy of your system. Then I look at this. Now for part A, there's no friction. What's the only thing doing work on the crate for part A? Is the spring. If the spring is the only thing doing work, then well, spring is a conservative force. That is, we conserve mechanical energy. So therefore, this is equal to 0, and therefore we can say that the initial energy equals the final energy. Well, what is the initial energy? Well, the mechanical energy. Well, remember that mechanical energy, right? I'll just write it here. E equals the kinetic energy plus gravitational potential energy plus elastic potential energy. That's the definition of mechanical energy. Now, in this problem, everything's at the same level. We're not changing height, so there'll be no change in gravitational potential energy, so we don't need to worry about that. And then for the initial energy, it's not moving. The initial velocity is 0, so the initial kinetic energy is 0. So we have no kinetic energy. So all of the mechanical energy, the initial mechanical energy is elastic potential energy. That's my initial energy. And then once the spring is back at its relaxed position, the energy is now kinetic energy. So that's the kinetic energy there. So we said, hey, just the potential energy in the spring is going to be equal to the kinetic energy of the crate once it gets moving. Okay, does that make sense to everybody? That chain of logic? We're just seeing where we're accounting for the energy. So this is 1/2 k x squared, or you can call it delta x squared if you want. And then k is 1/2 m v squared. So now all we need to do is solve for the velocity. The 1/2 goes away, and so v is going to be equal to k over m. I'm going to divide by m times x squared, and then we're going to take the square root. And now we can plug in our values. And k was 500 newtons per meter. The mass was 20 kilograms. And x was 0.3. You can put negative 0.3 in there if you want, but it's going to get squared, so the negative's going to go away. And so from that, when I plug in my values, let's see, 500 divided by 20 is 25 times 0.3 squared equals 2.25, and then we're going to take the square root of that, and I got 1.5. Do you agree with that? Other people get that? So V equals 1.5 meters per second. That looks terrible. 1.5. Any questions on part A? Right? The energy goes from the spring into the kinetic energy. Now, part B is a little more complicated. So let's do part B. So the work done by a non-conservative force will result in a change in mechanical energy. Now, this right here is the work done by friction. And so this is going to be the force of friction. I think the work done by a non-conservative force. So let's go up here and look. Let me zoom out a little bit so I get more of the paper. If I look at this crate while it's being pushed, I've got this force of the spring. I'll call that F sub S. But we also have this force of friction that's pushing back on it, right? I mean, the spring is pushing to the left and it's displacing to the left. To the right. It's displacing to the right, but the force of friction is pointed to the left. So the work done by the friction is the force of friction times the displacement. Well, we're going to go from here to here. So we'll just call that delta x, and we'll plug the values in a minute. But what is true about the force of friction and the displacement? They're in opposite direction. That is cosine of 180 degrees. The magnitude of the force, magnitude of the displacement times the cosine 180, because they're in opposite. So friction is doing negative work here, and that makes sense because negative work means we're taking energy out of the system. We're losing mechanical energy. Friction turns everything into, the random motion of molecules and so on. Now that's going to be equal to E final minus E initial. Okay. Now, this is going to be kind of long and now what is E final? 1/2 mv squared, right? That's just like what we did last time. The final mechanical energy is going to be in the kinetic energy of the moving crate. Minus the initial energy. What was the initial energy? It was all in the spring. 1/2 k x squared. So we've got to solve this long, ugly thing right here. This equals this. We got to solve for V. And so it's kind of ugly. Well, let's break it down. Let's figure out what the force of friction is. Force of friction is equal to mu times the normal force. Well, let's look at this object here. We've got gravity pulling it down. We've got the normal force supporting the weight. So the normal force is just equal to the weight. So this is mu, which is 0.3, times the normal force, which is just the weight. 20 kilograms times 9.8 newtons of force per kilogram of mass. Or you can use meters per second squared if you like. So let's just go ahead and calculate these as we go. It's a little bit easier to understand if we do it that way. 20 times 9.8. And I got 58.8 newtons. Now, that's the force of friction. Now, let's figure out how much work was done by friction. Because now we know what the force of friction is. That's 58.8 newtons. Times delta x. Well, it went from here to here, so that's a displacement of 0.30 meters. Cosine of 180 is -1. So, see, times 0.3 equals, and I get 17.64, negative 0.64 joules. A newton times a meter is a joule. Okay, so we know that's the work done by friction. It took that much energy away. Now, let's go ahead and figure out how much energy it had to begin with. The initial energy, which was 1/2 k x squared. And so that was the energy that was stored in the spring. So 0.5 times 500 times 0.3 squared. And I get, we get 22.5. So look, here's what this is saying. We started off with this much energy stored in the spring. Friction took this much energy away. So how much energy is left to be kinetic energy? Well, let me let's take a look at this. I have to do this on a separate sheet. I'm going to rewrite this whole ugly thing right here, except that I'm going to use the values we got. This right here is the work done by friction. That's negative 17.64 joules. Okay, and then equals, now the final energy, that's what we want, has what we want at 1/2 mv squared. And then minus the initial energy we had, which was 22.5 joules. So we lost this much energy. We started off with this much, and so whatever we get is left over for kinetic energy. So let's solve for B. First of all, I'm going to add 22.5 joules to both sides. And let's see, I get, plus negative 17. I get 4.86 equals joules equals 1/2 mv squared. So solve for V. So that's going to be 2. Right, multiply both sides by 2, 4.86 joules. And then divide by the mass, which is 20 kilograms. And then I got to take the square root to get the mass. I'm off screen. Okay. And we at last have our answer. And you get 0.697 or 0.70. That was hard. That was a hard problem. Okay, at least part B was. Let's zoom out and look at the whole thing together. See if I can fit it on the screen. Just barely. You see, actually, it's not that much. I mean, algebraically, it was harder. Maybe there was a more efficient way of writing it down than I did. But in part A, there's no friction. So there's no change in mechanical energy, which means the mechanical energy I started off with is going to be equal to the amount of mechanical energy I end up with. And that allows me to set up this equation and easily solve for B. But in part B, we had friction. And that friction took energy away. So that this is the energy, the change in energy, which is equal to E final minus E initial. And then we just had to do a whole lot of algebra, mathy calculations and to solve for velocity. Okay, but it's messy and tedious, but it's not that hard once you see it. Okay, any questions? Okay, that is all.